Welcome to this simulation of an emitter modulator circuit for amplitude modulation. Here, you can see the complete circuit, including the two N3904 transistor, biasing resistors, coupling capacitors, and the signal sources we'll be using for modulation. Next, let's focus on the signal generators and the oscilloscope, which is positioned on the right side of the screen. On the left, we have a carrier signal generator set to a frequency of 5 kHz and an amplitude of 1 volt peak to peak. This signal is represented in blue on the oscilloscope. Below it is the message signal generator, configured to a frequency of 1 kHz with an amplitude of 3.5 volts peak to peak, shown in yellow on the oscilloscope. Now look at the red waveform. This is the modulated signal, the result of modulating the carrier with the message signal. Notice how the red waveform's amplitude varies in sync with the yellow message signal, creating a classic amplitude modulation effect. Here, I've adjusted the waveforms on the oscilloscope to better align their amplitude levels and timescales. This makes it easier to observe the relationship between the signals. The yellow waveform shows the message signal, which is modulating the amplitude of the blue carrier signal. The resulting red waveform, the modulated signal, clearly shows how the message signal's amplitude is mapped onto the carrier's envelope. Now watch closely as I vary the amplitude of the message signal. You'll see that increasing the amplitude of the message signal directly increases the modulation depth of the modulated signal. Similarly, reducing the message signal amplitude decreases the modulation depth. This demonstrates how the message signal controls the carrier's envelope. Here, I've adjusted the timescale on the oscilloscope to zoom in on the modulated signal. Notice how the red waveform becomes clearer, making it easier to observe its detailed structure and the modulated carrier frequency. This helps us analyze the modulation effect at a finer resolution.